But what is there in audio signal? What terms are there? What physical terms are there in the audio signal? Is anybody there?
Yes, sir, we are here. So,
Okay.
amplitude, frequency, and spectrum.
What is spectrum?
It is the range of how the audio is coming, the audio range.
Can you give me an analogy or equivalent spectrum in a image or a video, context?
So, generally, we talk about the light spectrum
How?
and
What is that? Any specific example from the light spectrum?
different frequencies of the light will
Yes.
have
What,
different
what is
colors.
the manifestation of that? How it is manifested in
Colors,
spectrum?
colors.
Yeah, yeah. No, what is the manifestation? Colors is a theory, right? Manifestation is you have seen that rainbow.
Yes, rainbow, and
Is it a
even if we,
spectrum?
yes, yes.
Right?
So, audio
So
also will have a range.
what is meant by that? Audio has a spectrum.
Basically, when we say this is the range of sounds we can hear, so for example, a bee humming, um, uh, some of them can hear, some cannot hear, but a human speaking we can hear. The spectrum in which the human talk we can hear it. Maybe some other organism, what sound it makes we cannot hear it.
When do you get a sound spectrum?
When there is a kind of vibrations that happens inside the ground when we are doing the tune.
Anywhere. For that matter, you will get spectrum for any audio signal. Any physical activity will have a signal, right? That is likely to be there. What causes that? When you get that, you're right. Can you change that vibration to something else? Vibration is correct. Vibration of what?
Vibration of the
Uh,
air particles, like what I mean to tell, there is a medium that which we are trying to
The sound is not a
generate
particle.
that vibrations. That
Sound is
vibrations
not a
is,
particle.
sorry, sir.
Sound
It,
is not a
it can
particle.
be a pitch, it can be a diversity of the vocal or loudness.
Loudness is not spectrum. Loudness is not spectrum. It is resonance. So when 10 people sing the same song with the same tempo, the sound is very high. The energy is added and you can hear for a long distance, right? So basically it is vibration with multiple frequencies. When it is heard as a single signal, we call it as a spectrum. Like, white light is split into 7 different colors, right? A audio can be different, split into multiple frequencies, and that is called as a spectrum. So now this spectrum is one thing which can be used for signatures, which is called as voice signature, which can be audio signature. Now you can start comparing that. You can use now you can go for empty CNN also, multitasking CNN, to compare audio signatures when it is converted to an image. We will see that how do we convert that. And one of the work that I'm currently doing is that can we make sure that it is 100% this person? How do we do that? We don't know whether we succeed or fail. Certainly, we would like to do that. Spectrum is one of the things that you have to understand better. Oh, what are sound waves? Right? Sound waves basically is a spherical wave. So you have to understand that. When I speak, does it mean that the sound travels only in the forward direction as has been shown in speakers? Can't
no,
the
sir.
person standing behind me here can't hear that?
Yes, it is. It is all around that goes.
It is spherical. Somebody who is standing above me, standing below me, standing to the left of me, in front of me, right of me, behind me, everybody can listen what I am speaking. isn't it?
Yes, sir.
Right? And the second thing you have to understand is the acoustical energy is uniform in all directions. The intensity with which it sends it, right, is uniform in all directions. But why the person sitting behind me cannot listen to it as much as the person in front of me? Have you seen this phenomenon?
Because of obstacle,
What is that obstacle?
we are the obstacle.
Sorry?
We are the obstacle, our body.
Not our body.
Direction of the wave.
Direction of the wave is same in all the directions. It is the
The
friction,
absorption of the energy by any object.
air. Propagation of this energy by air in a backward direction is less compared to forward direction. That is the reason when you are talking against the air, the person behind you can hear better than the person standing in front of you. You can try this. Put a fan in front of you, right? Put it at 5 and run it and speak now. The person ahead of you, a meter ahead of you, let him ask how clear you are. And person 1 meter behind you, ask him how clear your sound is. The person behind you will tell you, I can hear you. The person in front of you says that, can you speak louder? Can you increase the amplitude so that the energy is more when it comes to me? Right? So we would like, in fact, in sound engineering, these are the principles they try to use, right? And make sure that the effects, most likely the pleasure effects or the pain effects, in terms of, let's say, if you are seeing exorcist, right, the sound itself is scary. Movie is not scary. If you watch the movie without sound, it has no effect. But use the movie, use the sound and watch the movie, right, we will pant. Right, most of the kids I have seen, they do not want to see that movie because of the sound, not because of the movie. Right, it's not rock, but the way in which it has been given is good. And the binaural and others is a technology where you can give to the left ear, you can give to the right ear, and you can combine that, and you can see what is the effect and all those things. We are not getting into sound engineering. We'll not get into that. We are not experts in that. We just read. It's all Google knowledge, right? Nothing more than that. But the problem, like, can this be used as a biometric, is what we are looking at. Is what we are looking at, right? And if you look at it, a small decrease in the sound pressure, right, will always be when the distance is doubled. So there will be a decrease whenever the distance increases, the energy propagation, because it is going wider and wider in the spherical way, not in a straight line like a laser. So its energy reduces. It's not necessary, but we should understand when to speak, because where this will be used, you would like to listen from 10 meters. So you should know what kind of compensation that you have to add when you listen to a sound from 10 meters, or you listen to the same sound from 1 meter, where your precision will be higher.
1 meter.
Yeah. Now, how do you compensate anything that I heard at 10 meters? Can you
Uh,
increase the intensity by sampling, by augmenting, by doing other things, and look like it is near 1 meter? And that is the thing that we are interested in. How can we do that is what we are interested in, right? Whether a person can listen or not is not my problem. Now my problem is, when I listen, is it a signal for safety, or is it a signal for no safety? If it is a signal for no safety, do I know what I have to propose? If I don't know, immediately I shut down all the doors. Right? Jurassic Park. Close the doors immediately. When you cannot do anything, you must be in a safe position. So these are some of the applications that we are looking at from the sound waves. Now look at the sound waves. Right? How many times it happens in 1 second is frequency. This is the amplitude. And how many frequencies are there is our spectrum. Are you getting the point?
Simha sir, I had
Yeah.
one doubt regarding the biometric.
Mm.
So when we have to use an aspect as biometric, it has
Mm.
to remain constant. For example, we use the fingerprint. The fingerprint is
Yes.
constant. So there are two aspects. It is constant for a person, and it is different from everybody else. So it is
Mhm.
unique to that person.
Yes.
So when we talk about sound as a biometric, um,
Not sound. Not sound as a biometric. Voice as a biometric. Sound is not a biometric.
okay, our voice as a biometric.
Yes. Yes.
So,
Yeah. But
regarding the being constant, so like how a fingerprint is constant, our voice may not be constant, because when we are angry, we will be talking in a different way. When we are whispering, we will be doing it in a different way. So, how
mm,
can we use it as a biometric when it is changing?
yeah. So there are two ways in which we try to analyze this. The first is called as text-based. The second is called as the non-text-based. When it is text-based, I want you to tell me what is your name and what is your father's name, what is your son's name, what are you doing. These are the four questions you have to answer very crisply in 3 or 4 words each. Right? It is text based. I am asking you for a text and you speak, and the signal for that is very specific for you. You can bring an imitator, but the imitator characteristics are different from your characteristics.
Okay, I understood. It's like speaker recognition. Like when we have Alexa, so there is speaker recognition that it has to do. It has to identify who is talking. If there are three or
Yes.
four people in the room, it has to know who is talking. So initially, they will make us speak some stuff so that it can register that it is our voice and recognize us when we talk next. Okay, I
Yes,
got it.
yes, it is speaker recognition. The second part is purely acoustic characteristics, not the text characteristics, but the acoustic characteristics. That will be useful when you told, I'm angry, I speak in a different way. I'm sad, I speak in a different way. I'm happy, I'm speaking in a different way. Right? And all these things, certain characteristics are invariant. Right? Certain frequency of your sound is invariant. We are hunting those frequencies and matching with your current speech.
Okay, sir.
What are those frequencies which are invariant? Can I match that with the current frequencies which are invariant? If both of them are matching, the match may not be 100%, but certainly anything more than 90% is likely to be a match. False
Okay.
positives are very, very less. That's why we don't find many mimicry artists, right? We
Yes.
recognize
Yes.
that he's a cheap imitation.
Yes. Yes.
Right? Otherwise, still I had to listen to one PB Srinivas.
Yes. Yes.
Right? There was one guy called Atri, but that gentleman passed away untimely. Right? Other than that, I have not seen anybody capable of singing like him.
Got
But
it.
imitations are there. 50%, 60% imitators are there for PB Srinivas. SP
Yes.
Balasubramaniam, plenty of people are there. Even for Manna Day, I didn't find anybody. But Kishore Kumar, in fact, we used to compare even Kishore Kumar is like SP Balasubramaniam is like Kishore Kumar. Though there is a difference. Whatever Kishore Kumar would have done, SP Balasubramaniam would have done. But it is not so with others. So imitation is extremely difficult. So in fact, what we are trying to do is the problem, what Abhishek was telling, what Guru was telling in terms of music, learning music through AI and things like that is basically imitation.
Yeah, we imitate the teacher.
Yes.
We
So
imitate how they're singing. We listen to it and we copy it.
yes, actually, all bad habits of teacher also will come to us.
Okay.
So we have to accept it. There is nothing wrong, right? It is useful. What is the problem if you have bad habits, still you sing, right? You are better than me because you sing. I don't even sing, I shout,
Yes. Yes. I got
right?
it.
So we have to be very clear about how exactly we do that. Okay. Now sound waves, the amplitude is nothing but where the peak is happening, where the trough is happening. Most of the time this will be symmetrical, right? When we are going with music and other things, because most of the time music looks like symmetrical, right? But the usual talk is not symmetrical because multiple frequencies are there. Those frequencies are mapped and they are combined. In fact, I always see people, sorry, I am taking names, North Indian people, when they come to South, they mix sambar and chutney. I scratch my head. What kind of taste is this? Including my grandmother, they used to tell that never eat like that. You eat idli chutney separately, idli sambar separately. Now South Indians also started. First put idli into sambar, then take 1 cup of chutney and mix it and eat. Right? So that mixing is a different frequency. Sambar has got a different frequency. Idli has a different frequency, and chutney has a whether eating is wrong or not is not the question. It is not habitual for us is the difference. That difference can exist. That's not a problem. When multiple frequencies will be there, we try to get the shape of this in a different way. And that this alone is monotonous. Right? What is monotonous? Same sound. Right? That monotony is not good. Right? Monotony is good when we try to do something which is a white noise. Right? I would like to differentiate between signal and noise. I introduce white noise. Then I will try to introduce monotonous signal. A signal like this, a sine wave, a cosine wave, right? Only that will be given. And now I would like to check whether my system is capable of detecting this white noise and actual signal. And that is the real problem that we are interested in. The digital signal processing comes from a different perspective. So AI goes with a different perspective. So DSP goes with what is called as confirmation. We go with what is called as induction. For us, there is nothing. Somebody has told the sound hello is the word hello. I will try to see whether the spectrum, cepstrum, and all those things are matching with what is been given for the reference. If it is, then I will say this word is hello. Right? So there is also what is called as continuous speech recognition, which we'll discuss. We'll not touch upon it because it is too big a topic. Right? I will not touch upon it. If we can do the small word recognition, you can always do sentence recognition. It's not a problem. At the end of the day, it is recognizing words and combining the words with respect to something that has been spoken. That we will see. Sound waves contains these properties. What is sound? How exactly it happens? So when a microphone, a acoustic pressure waves comes, the microphone will collect and changes the electrical signals. These electrical signals are analog signals. And most of the time it looks like this. So actually the acoustic pressure is like this and your electrical wave is also like this. And there's a comparison. This can be converted to this. This can be converted to this. So on the other side, we will have speaker. Right? Speaker, the microphone will convert acoustic pressure waves into electrical voltage and the speaker will convert electrical voltage into actual sound. How good it is? That depends on how the sampling has been done. We will see all this sampling and other things. First, I wanted to give a big picture of everything that we are going to do. Then we will get on to hands-on. How exactly we do each and everything and not deep, maybe about 20% what is required for most of our projects. Subsequently, if you are interested, you can get deeper into it. Right, we can always connect and we can go deeper, but more or less in the hands-on sessions and all, we try to touch 20%, which will be using 50-60% of the times. Okay, mostly the feature extraction and things like that, reading the audio files, audio file pre-processing, classification, right? Then matching and things like that. This is what we would like to do. So once the sound can be created or stored, right? Now how we hear, what happens here? So the sound falls on this and the auditory nerve will get basically the signals. It converts that into this basically is the sound signal, right? Instead of electric signal, this becomes our electric signal. In fact, you have to understand our body is electricity. All our signals, though they say it is chemical, actually they are electrical. This electrical signal which is coming out of this is mapped with some kind of words or some kind of feeling that I have with that sound in my brain, and that will be interpreted. And this whole process is basically is a Fourier transform analyzer. Our ears are Fourier transforms. So they transform any sound into Fourier transforms. We'll see what exactly is Fourier transform. It is nothing but Fourier. Some 200 years back, he said that any continuous signal can be converted into sine wave. That is Fourier transform. Can you take any signal? It can be a square wave, it can be triangular wave, it can be a harmonic wave, it can be any type of wave. Can you convert it? Can you split it into multiple sine waves? That exactly is Fourier transformation. So our ear, it can take any signal, convert that into what I can understand. It's a natural Fourier transformer. We don't know whether it does, sine waves, convert everything into sine waves or cosine waves and do that. We don't know. But it does what the artificial intelligence system is doing, what audio analysis system is doing. This exactly is what happens when I hear something. And this is connected to my cognitive part of the brain where it stores the language. It does the reasoning and all those things. It recognizes what this sound means with association. Right? This is what we do. So once we do this, normally what happens is the time domain is not important for the human ears. What is important is frequency spectrum. We understand the frequency at a specific point in time, not over a period of time. That's why when Buddha said we live in present, our ears live in present, our eyes live in present, only our mind lives in past, present or future. That is the biggest problem we have. It is not the sense organs. They are very clear. They will get the signal now. How your ear can recognize what was there 5 years back? Can it do?
No, sir.
Can you see what you have seen yesterday?
No, sir.
Now, no, right? You store those experiences in brain and your mind start playing trick. I know this, I can do that, right? And everybody believes mind. Nobody believes physical organs, right? So we want to replace, we cannot replace this. What we are trying to do is, can I replace brain? Right? These are all already there because it's electrical signals, right? Now you can see hearing aids. What it does, it basically enhances the amplitude so that it can fall here. So any sound that comes on the electrical, the hearing device, right, will amplitude is increased and sent back. That's all, right? It's already there for a long time, right? Starting from mechanical to almost smart plugs now, which can be like a small Bluetooth. Nobody knows that you're dumb. Right, we are very happy to see that. Oh, why, when they ask what is that, we will say that I'm putting that plug so that air cannot go into my ear. Right? Nobody doubts that. That's good. Next is digital sound. What exactly is digital sound? What is sampling?
At different points of time, we check what is the frequency, what is the
No,
amplitude,
not
what
what is
is
the
the
frequency.
spectrum.
Frequency is fixed. We check the amplitude for each frequency.
Okay.
At every point in time, I will try to take this x-axis as time. At this point, I will go and check what is the amplitude. At this point, I will go and check what is the amplitude. At this point, I will go and check what is the amplitude. But for all post-processing, I will make this as a smooth curve. I'll make this as a smooth curve. The same thing is happening in your inverter, right? It tries to take the direct current from your battery and converts that into AC, but it is not a pure sine wave. Right? Somehow it takes all the frequencies that are coming and tries to adjust and filter it and makes it look like sine wave. So if you understand, all waves are sinusoidal waves. Are they truly sinusoidal waves? Not necessary. Not necessary. But that's where we are using Fourier transforms, which says that any wave can be represented in a sinusoidal fashion. Right? By adding multiple things, you can bring it into this. We will see how exactly we do this. Now what we try to do, we try to sample at different time ranges. I must give what is the spacing for time so that I can pick every periodically every time I would like to check the amplitude of this sound. Can you see any difference between this and this? Normal human ear cannot differentiate between this and this. Only when we try to take the spectrograph, we can see how exactly they look like. Only when we understand what is the sampling frequency or the sampling ratio, we understand how it is being done. Otherwise, human ear cannot differentiate. That's a good thing, that's a bad thing. That's the weakness of the humans, right? We cannot sniff like doctors. We cannot be sense like we cannot sense like snakes. We cannot do that and all those things. But always we do defensive programming. That's why we always call we are intelligent animals, right? We are very good in doing certain things. If I cannot recognize them, I will use a device to recognize whether it's a digital sound or analog signal, right? If it is analog signal, what happens? Some frequencies always be present. All the frequencies will be present in the analog signal. In a digital signals, I can do low pass filtering, I can do high pass filtering, I can do band pass filtering, and at the end, some of the frequencies might have died when it is transformed from audio to analog to digital signal. So that's why now it's a compromise. Why it's a compromise? You can go for 128, you can go for 256 kbps and things like that, right? But what happens when you convert this into 256? Now, this is continuous. It means that there are infinite number of points over a period of time, isn't it?
So, sir, if we make it 256, we are going towards the actual analog signal. It will be better than what we have at 64, what we have at 128.
When you can get the same result with 64 kbps, should you go for 256?
No, we will always try to go for the lesser one because sampling is expensive.
Sampling is not expensive. You can do sampling, right? You can do sampling, but the sampling rate, higher sampling rate is expensive. Sampling is not expensive. I take only sample at a point of time. It is something like every 1 second I will go there, measure the frequency, come back and write here. That's all. Or you can reduce it to 0.1 seconds, or you can reduce it to 0.01 second, or you can reduce to 0.01 second, which is almost a millisecond. Every millisecond, you can go and check what is the frequency or what is the amplitude. You can do that. You can do that, or you can do this, right? If the results of all the three are same, should we settle at this, or should we settle at this, or should we settle at this?
We go for 64 itself.
Yes, we go for 64. Now, if you ask me, most of the time, I tries to start with 64 or less than that. Right, I do not want to look at too many things. When the accuracy has to be improved, we say one of the possibilities increase the sampling frequency. Other than that, a sampling rate. Other than that, I never do that. It is not necessary. Right now, when I convert this back, this basically is called as coding. Right? Have you heard about codecs?
Yes, sir, audio codecs.
Codecs is nothing but convert this into sampling and encoders. The code and encoder part is the decoder. When you go for decoder, this will be converted to analog signal. So whenever you say that the codec is not available, it means that how this has been sampled, right? Or how it has to be interpreted is not there with me. That is the message that system is giving to us. My codec is not available. Yeah, coder and decoder is not available for me. So any device, any software, any sampling mechanism which does this, convert from here to here, from here to here is called as a codec. Coder and decoder. Yeah. Any doubts here?
So generally in Bluetooth speakers we have this codecs.
Hmm.
because it has to take signals and convert it and send it as audio signal for the user to listen to it.
Hmm. True. Codec can be anything, not necessarily just for Bluetooth. It can be for Wi-Fi. It can be for anything else. Even CD. You need a codec for converting the signals that are available in CD to the sound. You need a codec. If MP3 codec is not there, you cannot run the CD, isn't it?
Yes.
Codecs are always there. So codec is basically a digital signal processing problem rather than a machine learning problem. Machine learning never want to recreate the sound, never wants to. But when it comes to compression, now we would like to check whether the sampling is good. After sampling, can I go for K-means clustering? Can I go for spectral clustering? What you're trying to do now, let us say in a song, what are the two things or three things that are likely to be there in any song? Probably some of you may know, some of you may not know, but for the benefit of everyone, I would like to ask these questions to everyone.
We will have melody,
No, no,
rhythm.
I don't understand English music. If you can be, forgiving, can you tell Kannada music or Carnatic music?
Sir, music, it is a collection of swaras. So it's a
Song,
collection of
yes. You take a
frequencies.
song when you sing a song. What is that that you can see, right? Three or four main things that you can see in a song.
Highs, mids, and lows.
Highs, mids, and lows is only amplitude.
Hmm.
Okay. So every song has got what is called as charana, right? Which is nothing but something which will be repeated often, right?
Hmm.
And there is pallavi. I mean, charana is not repeated. Pallavi is always repeated, right? Right. Then we have what is called as the chorus, the background chorus where they will sing, they will try to add something.
Okay.
Recently, I was listening to one song, Namo Namo Maheshwara from Kedarnath. Right? In that movie, that Namo Namo comes often, and somebody in the background will sing Bole Shankara, something like that. Then some part will be there which is not repeating. Now, can we segment all of that using this sampling? Can I segment without knowing that it is Pallavi, Charana, and chorus? Can my machine learning detect that? Unsupervised learning. Can you see how we are trying to apply the machine learning, the deep learning, and other things what you have studied, right? Here,
Yes, sir.
in fact, I would like to use a 3 or 4 node autoencoder, right? I will have all the signals from the codec, right? I will try to give first layer the inputs. The second layer will contain only 4, right? And the third layer will be recreation of the first layer. If it can do the entire music, it can be recreated. The 4 I can identify, okay, these are the important ones. This is how it is segmented, right? All of this, anything that we are doing with structured data, we can do with unstructured data like audio signals. So your projects can be something like, can you take that? In fact, putting a song, a 5-minute song is huge. Why? Why it is huge? The data set that you get, the amount of data you get is huge, huge. Why? It is a time series. It's an infinite time series. Unless you sample, your data is not good. Now, if you want to sample, what happens? You have to look at the window size. And that is where the domain knowledge comes in. We're all bad. My, music knowledge is Google knowledge or AI knowledge, not exactly how musician thinks. For me, the way musician thinks is wrong because it is not useful for me to learn as fast as I can. No, until it is perfect, he will not use it. Boss, I don't want to be perfect. Just I would like to listen to the music, and if it is soothing, I would like to relax. That's all. And I would like to sing the same song with, if not 100% imitation, I would like to do that with 50% imitation. Can you measure that? Match. How much is the matching when I sing the same song? That's another application of what we call as the machine learning. We would like to see that. So this is the digital sampling. Digital sampling will help us to reduce the dimensionality, isn't it? Will it reduce the dimensionality?
Okay. Yeah.
Tak, 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 tak.
What?
People are here. Do we reduce dimensionality?
वो तो सारे क्लियर है आपको कैसा लग रहा है कि वो डिविजन
Only Pawan is audible.
sorry
No, 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 Pawan. You can keep it on. Because for me, it is a white noise. No worries. So, why the sampling is a dimensionality reduction technique? Forget about audio. When you have 1 million customers, 3 variables, 1 million records, if you take 10,000 records, are you reducing the dimension or not? You're getting the point. Hello, am I audible?
So dimensionality reduction is about the features, right?
Where we said it is feature reduction. We said dimensionality reduction. Dimension can come in two ways, right? Number of records and number of fields. It is not just number of columns. It is also number of records.
Okay, okay.
Now, why do you want to know every candidate there is a girl? Right? You take sample, 90% of them girls. There's a possibility 100% of them will be girls. Right? So there are two ways of dimension reduction. One will be in records, one will be in columns. When you do column reduction, it is called as feature selection. Right? When you try to do it across records, it is called as segmentation or compression. You compress 1 million record into 10,000 records. Is it not dimension reduction? It is. It is dimension reduction. Right? So you try to take, for example, MP3 is a compression. Right? Sound will be compressed. You digitally take it and compress it. You sample it and compress it. When you, play back, the user or the audience will not recognize that it's a digital one. And now people have accustomed that they want only digital music. Earlier, my father used to tell I should learn harmonium if I had to learn music. And now they say, no, no, no harmonium. Go for digital keyboard from Casio. Right. If you can recognize the sounds are very clear, it becomes very, very clear, and it's data compression. Data is compressed and digitally given. So we have to look at that. These are some of the use cases of sampling. So once we will see how we do sampling, and sometimes we may do undersampling. Right. Undersampling is most of the time is the case. If they can recognize I'm expecting this, but you're telling me this, they are very good. They are domain experts. But if they cannot recognize, they are ordinary citizens and cannot see the difference between a good music and a digital music, they may agree both are same what is there. Right? So undersampling is always done without much of loss. It is lossy compression, but there is also what is called as lossless compression using entropy, but we'll not touch upon that because that comes under DSP. Yeah. Now, the next concept we would like to understand is the concept of window. You want to analyze how long the Pallavi will be sung, how long the Charana will be sung, how long the chorus will be sung. Do you think that when all of them are speaking in their own voice, you can recognize what the music is, what the song is? It is chaos. Nobody understands, nobody recognizes what they are singing. Right? But now let us say that everybody in unison, right? When the chorus has to sing, only the people behind will sing. When the male voice has to sing, only the male voice will sing. The female voice only will go for repetition of some first 4 lines, right? 3 times. And in between two, right? The different lyrics will be there. Can we recognize that without anything? And that requires clipping. What is clipping? Clipping basically is windowing. So window can be in vertical, window can be in horizontal. When it is horizontal, we call it as window. When it is vertical, we call it as clipping. Right? Normally, we are looking at what is called as a zero crossing line. That's one of the features that we would like to extract. One of the question was, will it change? Zero crossing level of any frequency is not going to change whether you are angry, whether you are happy, whether you are sad, or whether you are sarcastic. So what is the zero cross level of certain frequencies is what we would like to see. Zero crossing level is nothing but taking the average of all the signal amplitudes that are available to us. For a particular frequency, if I take it and try to compare that, it becomes what is interesting. So zero crossing level is one of the features that we are interested in. Windowing is another feature, another method. Basically, it is a kind of sampling, or it's a kind of portion of interest that we are interested in. Whether this 2-minute clip of the sound is different from next 2 minutes clip of the sound, next 2-minute clip of the sound. If it's an Indian song, normally we try to take it around 20 to 30 seconds window. Right? Most of the time, the 20-second window is different from 40, 60, 80. Again, another 20 will be repeated. So first one, the fourth one, and maybe the eighth one will be similar. The other two are not similar. So probably we may have 3 clusters. The first cluster will contain the 20-second, the 100-second, the 160-second content will be in one segment. The 40, 60 is in one segment, and maybe 120, 140 in another segment. So totally will be about 3 segments. We can recognize that, right? And that's a 30-second window. If we change the window, there is an overlap of the continuity into the window itself. So we had to optimize the window. When we try to do audio analysis, window size is very, very important. That's why we want to make everybody like machines. Don't try to tell me in a open way, right? It's not an open-ended question. What are your interests? Anybody can tell me what are your interests?
Hobbies, sir? Interests?
What are your interests? It's an open-ended question.
Okay.
What you have asked me is a close-ended question. So you are trying to make me a digital one. I am trying to make you an analog one.
Yes, yes.
Right? When you ask, is it hobby? If I say yes, you will tell my hobby is fishing.
Yes.
Right? Everybody is trying to, they say no, be crisp, come to the point. No, human should not come to the point. That is not human. Right? Only when a clarity, when a call for action, when some kind of groove has to be made, you have to be to the point. But in general conversation, you have to hide a lot of things. That's a different discussion altogether, mostly philosophical, non-technical, right? But the idea is we would like to go for windowing. You should not do too much of open-ended questions. We have to restrict where exactly this is likely to be visible. How do we start with that? We start with the Bayesian belief. If nothing else, okay, let me start with 30 seconds. I will check 20 seconds, 10 seconds, 40 seconds, 50 seconds. In any of this, if it is not available, I doubt whether it is available in 60 seconds. But if something is available, then I will fine tune whether the window size should be 60 seconds, 2 seconds, 5 seconds. What is the window size? I would like to analyze that. And that is adaptive. You have heard about recursive partitioning, right? When you do decision tree, right? Normally you try to do the recursive partitioning. You will take what happens when age is 1, age is 2, age is 3, right? What is the risk? You try to measure at every age level, you split above or below. How many are there? And you try to find the entropy, right? Based on entropy, you try to group it. And that is called as recursive partitioning. Same recursive partitioning we try to do with the window size. At what window size maximum signals are visible or maximum signals are available? That analysis we would like to do. The two techniques we use for that will be clipping and windowing. Getting the point? When I try to sever off some of the signals in the vertical direction, we call it as clipping. When we do it in the horizontal direction, we call it as the window. So clipping and window are two important ones, right? Normally, for example, clipping is one thing that we would like to see. Um, have you sung for any karaoke music?
Yes, sir. So we will get
Because
a tune there and we will sing the words.
how do you get that music? You get that performed by some artist, record it and give it to you, or you try to eliminate the human voice in the original music and try to take only the original music and give it. Which you feel is better?
People perform, sir. So they will listen to the song and they will perform only the music so that others can
So
sing.
I understand now why you are taken the ethical AI. Right. For me, people performing is not good. Right? Do you think they can perform? They can do it like a maestro, like Ilayaraja? When he's standing there, everything will be almost picture perfect. Right? Using that song and that music is much better than locally doing something similar to that.
Yes, yes. So if you see in any of the karaoke music that we get in YouTube or something, it will be a miniature version of what is actually there, because we cannot do all those instruments, all those, they will have lot of processing when in an actual music that is there. So only a miniature version of it they will play just for us to it cannot match what they have done. So as you said, if we can eliminate the human voice and take just the background music, then that will have all the components of it.
Oh yes, that is called as voice removal. So you can just take because the guitar will not play with the same frequency and amplitude as a human voice. So I have to just detect what is the frequency and the amplitude at which human is singing and suppress that voice. Then you get your karaoke music. You got it,
Yes, sir. Yes, sir.
right? You either clip it, window it, or do both and try to get your music out. Yeah. Okay. Then there is something called as quantization. Like I was telling, can you compare, can you get segments out of these sounds? That is nothing quantization. Quantization is nothing but binning. Can you bin it? Right? You can bin it. You can bin it. Right? A square wave is, can this look like a sine wave or a parabola? Or do you think this is square wave, one imposed on the other?
So it is digitization. So it's based on the sampling rate,
Yeah,
sir.
digitization itself is a quantization, but you try to do further quantization of the digital signal. You group all of them. As long as it is like this, I would like to take this as this. Approximately, it is this. Original is this. Approximate is this. This can be a next level of approximation. This can be next level of approximation. This can be near perfect approximation. Do you need this? This comes at a time complexity. This comes at a cost complexity. This is easy, isn't
Sir.
it?
Yes, sir. First one is
Very
easy
easy,
to do.
right? Is it good for all the purposes? No. Right? For some basic purposes, this may be good. For fine tuning, this may be needed. So it depends on how much money they have. Like the difference between Geo phone and the Apple phone. Right? In Geo phone also you can speak, you can do all those things. In Apple phone also you can do all those things, but the quality differs and you pay the price for that. The quantization is basically segmentation or binning that we would like to do. This is another concept that we would like to understand, right? So how do we sample, right? Normally in the phone, we try to sample at 8 kilohertz, right? CD is 11, right? Generally, most of the time we try to go at 44.1 kilohertz. This what we are looking at. And how many bits that we are looking at? It can be 8-bit representation or it can be 16-bit representation. And there is what is called as channels. So mono, stereo, quad, or some other thing. Like if it is mono, there is only one speaker. If it is stereo, Your left speaker is different from right speaker. You will hear in fact, both of them at the same time can give the same sound, right? Or they can give different sounds to different ears to give the different experience. The first one is called as stereo. The second one is called as binaural, right? Then there's quad, right? Normally, when you try to put it in a in an auditorium or possibly in a hall, right? You have to make sure that the speakers that you're putting there, right, will not do echo or will not create chaos and things like that. You have to put the speakers in such a way that the energy that is dissipated towards the audience is very systematic. I'm not telling symmetric. It must be systematic. Everybody should be able to hear the same sound at the same amplitude. That's not possible. That's a different thing, but that's where the effort goes to. So we try to say that at least 50% of the amplitude should be audible to everybody. So that's where we try to go for quad speakers and things like that. Even in cars, we try to put the quad speakers. But the problem is we really don't know we are using quad speaker capability or not. But if we hear, I have heard so many times that in my car, when I listen to something, it really has the quad effect. Only right or only left or all the speakers will be doing that. That depends on how you set all those things. These are some of the parameters that we are looking at. You cannot take a stereo from a mono. If it's a mono channel, it will be mono channel. But if from stereo, you can convert it to mono. A quad can be converted to stereo. A quad can be converted to mono. Most of the time, we would like to do at mono level only, not at stereo level. Right? Because our applications are practical applications. We are not here to improve the sound quality of the sound. Rather, we would like to detect the anomalies. We would like to detect the similarities. We would like to give the feedback. So in such cases, mono is more than sufficient. Right? Though there are groups in European and US universities who are working specifically on applying AI and sound engineering. Our interest, at least the way I'm working, is not in sound engineering. It is mostly practical applications like speaker verification, not recognition. I recognize Yashashwini speaking. Can somebody imitate and say I'm Yashashwini? Can I verify whether she is Yashashwini or not through the audio biometric? Absolutely, it is possible. That's the kind of application that we are looking at. Yeah. Next sampling
Sir,
is.
I
Yes.
had one doubt
Yes.
regarding mono, stereo, and quad. So this
Hmm.
is something that an artificial component generates. So can a human create a stereo or a quad effect?
No, no.
Okay.
So stereo effect is multiple sources of sound. On a lighter side, yes, human can create stereo effect, right? He can shout on one hand and jack the person in kade. So he is
Oh,
creating the stereo effect, but that is not because the metallic sound is different from the voice sound. When you go for a stereo effect, both the speakers will be having the same source. I mean, the same content, not different, isn't it? So human creating it is pretty difficult. As far as I know, it is not possible. But if there are some exceptions, good to see. Right?
oh,
Stereo effect is purely engineering one.
okay. So none of the nature sounds can do it, like an animal or a bird or an insect. None
Or
of them can.
two, three birds, one on the left side, one on the right side, calling each other, you hearing that may create a stereo effect.
Okay, okay. Got it, got it.
Yeah. Okay. So there are different rates of audio data. Normally, for most of us, I'll be working only with the archive waveforms. It is uncompressed because I don't want to compress, do all those things. All of this netcasting, preview, and broadcasting and other things, they go with different way, MP3 or real audio, so different type of things. But we are looking at waveform. That's why when we try to do, I'm not interested in analyzing 100,000 hours of information. I'm not at all interested. I'm interested in 10-second information. Tell me your name. If your name is matching, my work is done. That's my problem. That's my audio analysis. Right? We try to work with wave format. right? The PCM format is there, but mostly we work with wave format. So you can get into the details of each of them, look at that and do all those things, right? But this is meant for actually, a real audio, which is be going on the broadcasted phase in internet, right? Compare this with this, right? Almost 70 times, so not 70, 80 times, right? 80 times more than this, but this I cannot analyze. Unfortunately, people cannot recognize when I speak, when I transmit this, because they are looking at the content rather than the voice, isn't it? When you listen to what happened in Ukraine, when Russia bombed it in Vian, are you looking at how Palki Sharma is speaking? What is her pitch and what is that she is telling? Or you are trying to get the words that are there and the meaning of those words? What are you trying to do? In netcasting, are you interested in voice quality or are you interested in the content?
The content mostly.
Content. When you are testing this, are you interested in the content? Are you interested in the voice quality?
The voice.
Yes.
They're
So
saying.
this is a spectrum of analysis. Most of this will be done by sound engineers. Though they can use AI in different ways, most of us will be working in this area. Yeah. Any doubts here? Okay. Right. There are many sound formats, and what we are working is only the wave format, which is from Microsoft, and it contains a lot of things. It's of no use to us unless you are writing program in C. Most of this handled by Python for us. If I use PyAudio or if I use Librosa or if I use audio, right, any of this package will handle all of this. Only when I'm using C, I would like to see from where I should get the data. The data starts from hexa 2C. From there, the data is there. All this is metadata from hexa 00 to hexa 28, right? It's all metadata. And this is where the actual data starts. From here, we can see what exactly is the length, the data chunk, right? Length of the data chunk. So this plus this will give us how much is the data that's available for me, and I will stop at that. Right? We take this sample data starting from 0 to C, add the content of this length of the data, which is there in hexa 28 to hexa 2C. We will get the actual data addresses. So it is address based, mostly C, may not be necessary for us, but I wanted to show how it looks like. Yeah, you can look at this and you can check everything. So all of this metadata you can get from Python also. Or do we need it? We don't need it, right? If it is not read properly, it says that there is an error and pass back the error to client. Or if you're doing it in batch, if that is not done, what you do with missing value in structured analysis? If there is a missing value, what are the options you have?
You can replace with the null. I mean nan, not a number.
Yes. Yes, that is one. Second,
Average of all the other in that column.
that is replacement.
Replacement.
Replacement can be any technique, is one form, one possibility. What will you do? Something else you will do, right? You will drop the records,
Drop. Remove it completely.
right? Drop NA is your first method, right? Keep the original data. Drop NA is the second approach that you have to do, right? Then all imputation and other things to compare. If after doing that along with the original data by dropping all the records, if the model is same, then your replacement is correct. After replacement, if you get a different answer, your replacement is wrong. Dropping is better. Okay. So in this case, we try to drop it. If there is no data, drop the file. You should not impute anything in audio. Only when you are decoding, you can impute in audio because you want to make it smooth. Otherwise, you won't. Okay. So what we are doing, in fact, already it's a pretty old one. Digital radio, all those things are reality now, right?
So drop in the sense like in this audio we are dropping off the silent this one.
No,
That
no, no, no,
when there
no. You
was
are not able to open the file. Drop that file. Once you open the file, you can do a lot of things. If you can read a file, you can do a lot of things. When you cannot read a file, you will not bring that data as a record. In the source itself, we will drop it. Not after bringing it and putting it in a format.
Okay.
Yeah, okay. So I will not get into this. Right. Basically, if you look at how it all started with somebody thought that if sound is energy, sound contains signals, it must be some kind of amenable to analysis. Right now, they started with, okay, if you speak like this, all of this is time. In x-axis, it is time. Right, what is the minute, and each of them, or second, this is the second, and how it has been spoken, each of that is a signal. It means that any acoustic data is a time series signal, but it's a complex signal. It is not simple time series like our sales forecasting or possibly emission forecasting, blah blah blah. It is not. Right, the average may look like this, but it contains multiple frequencies. That is the complexity. The complexity of the sound wave is, unlike time series, it is not univariate time series. It is a multivariate time series. Multiple frequencies at multiple times will be there. All of that combined together will become a sound. And that sound is unique. At least for people, it is unique. For persons, even for animals, when it growls, the growl of one lion is same even when he's old, and when it is may not be too young. Right, too young it is difficult, but when it reaches a maturity age till it dies, it remains same. That is what we are exploiting. So if it looks like a time series, can we apply time series methods? No, no, not all time series methods are applicable. Some time series methods in terms of clipping, which we call as the filtering, band pass filtering, right? High pass filter means any frequency that is above this 10,000 is allowed. Only that sound will be visible. Low pass filter is anything that is zero is allowed. That sound is allowed. Band pass is anything between 50, minus 50 and plus 50 allowed. Anything else is not allowed. So if you want to detect, is there a speech? Is there a silence? I can just look at the amplitude. Just look at the amplitude, apply the band pass filters. You will get whether it's a noise or it is no noise, silence or speech. That's an important thing, right? Can the machine learning do better than a simple low pass filter or band pass filter? That is one problem that we would like to address. How can we do this? Can you detect the silence and the speech periods, right? Forget about conversion. It is whether somebody is speaking or not, you should know, right? Gopi is working on one project where when somebody speaks, the system automatically recognizes the silence as I have to answer back. It is not. The question is not yet complete. How do I know that the question is complete? Alexa, Google, everybody has made very clear. So you have to start the button and stop the button. You say, Alexa, what is it? Alexa. So then it knows the start word and the end word, begin and end is there, in between is the thing. Let me analyze, let me give the answer. It speaks back. But in our case, we are not. We have to detect the silence and we have to detect the end of it. That's one of the applications that we can think of and pretty easy to implement quickly, right? Next thing that we are interested in is sampling. So they understood that it is not necessary if there's a possibility that a sound wave can be converted to an analog electrical signal. There is a possibility we can do the sampling. There is no need to store everything. In fact, in the beginning, there was no storage. It was just a concept. Then they understood that all these excitations to convert electrical signals into some kind of physical tracks led to what we call as gramophone recorder. We had the plates, and the plates, there were grooves, and when the needle was moving in the grooves, the electricity was varying, the voltage was varying. When the voltage varied, the speaker used to pick up that voltage, and mostly it will be kind of smoothing out. Once it is smooth, then the voltage is out, the speaker will sing the song for us from the disc. And that exactly started the whole sound engineering thing. But as soon as the AI came, sound is no more the engineering stuff. Sound is there everywhere. I want to say that for Siri, I would like to say, can you block my time for Monday 25th for a meeting? It is not a typing and things like that. It's a voice command. And we are moving towards that. We are moving towards voice enabled applications. Now, you can find a problem. A voice enabled application, it is been recognized and it says that go and rob the bank. It will go and will it do? What is the safeguard that you try to add there?
Biometric, sir.
No. Biometric, how? Oh, that this is your problem actually. It is ethical problem.
Yes.
How do you do this? Biometric, yes.
So only that person who is authorized to give the command, only that command we will consider.
No. That command should be in the global good. Otherwise, it will not do.
Okay, okay. Or
If it
like,
is not global good, if it is good for you, you say that go and rob the Reserve Bank of India and get all the 2000 rupee notes. It is good for you, but is it good for the global thing?
okay.
You have to define your ecosystem, and that context has to be established, and that becomes convergent AI. You will
What is
verify.
convergent AI, sir?
Yes. Yeah. So it's a convergent. It's a hybrid system, right? You are trying to combine 2, 3 systems. Text analytics system, then human machine interface, then acoustics or audio modeling. You are combining all these three. Yeah. Okay. So the next concept that we have to understand is spectral analysis. Right? Normally, the frequency gives the pitch, how long you can elongate it. Right? The amplitude gives the volume. Right? Most of the times, the volume is energy and the frequency is momentum. How long it can take? Do you remember? I don't know how many of you remember or seen or used. When we were young, we used to listen to Radio Sri Lanka. Anybody remembers?
How, sir?
Radio,
Sri
Radio Sri.
Lanka is a different country. Like we will not be able to get that here.
Yes, that was not the point. They used to give in all local languages of India. So from 3 to 4 was Kannada. We used to listen to Radio Sri Lanka. Radio Ceylon, not Sri Lanka. Right?
Yes,
That
sir. We used to call that as Ceylon.
Ceylon, Radio Ceylon.
Yeah.
Radio Ceylon was a short wave. Right? Akashvani is a medium wave. Right? Similarly, if you go for some others, right? There are plenty of though there's a frequency modulation and things like that, amplitude modulation and frequency modulation, but the frequency is basically short wave, medium wave, and long waves. Right? The short waves, the energy can go longer. Right? The long waves, the energy dissipates faster. It cannot travel far. Medium wave cannot travel far. The short waves can travel far. So we would like to do that analysis. The frequency gives the pitch, how far you can push it. The amplitude gives the volume, how much they can hear. So these two is what is understood in the spectral analysis. Normally we try to use Fourier transforms for building the spectrograms. And there is a opposite of this. It is called as, it is taken from CEPS, SPEC, CEPS. So one is called as cepstrum, another is called as spectrum. Cepstrum is actually opposite of spectrum. So it is inverse transform of the Fourier transform. So any data that comes to us, if it is converted to Fourier transform, we will get a spectrogram. And when this is done with inverse Fourier transform, we will get cepstrum or cepstogram. So we'll see that how exactly we build that. And there is chromogram, what kind of color is associated with each of them. Then we try to have correlogram, where instead of going with the frequency over time, amplitude and frequency over time, we would like to look at amplitude alone, time against time. We will see that also, how it works and things like that. Then coding scheme and other things, I'm not much interested. But basically, when we take up in the next session, we'll be talking about what is called as MFCC. Mel frequency cepstral coding. How do we code it? How do we take that? What exactly it is? This is nothing but another discrete cosine transform, like the discrete Fourier transform or the forced Fourier transform. Discrete Fourier transform is basic as a discrete cosine transform is basically taking it as cosine. It is taken in a different direction. So we will see that, right? Uh, Let me break here for some time. If you have any questions, we will see. This is what I told you about cepstrum and spectrum. Any questions? Please feel free. No questions.
Sir, so basically they are trying to recreate the sound, right? From the spectrum, they're going to the cepstrum.
Oh, no, 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 no. When you do that, you will not take the log magnitude. The spectrum's log magnitude will not be taken. You will just look at this. It is inverse of this log magnitude. It is not the spectrum. If you use the spectrum directly here, it becomes sound again. I'm taking log of the spectrum, and then try to go for inverse Fourier transform. And that is called a cepstrum. It has got its own uses. Why we have to do this? It has got some uses. Some signal comes out of cepstrum. We would like to see that.
So the question is why we cannot use the spectrum as is and why we need cepstrum.
Oh, we can use spectrum. We use spectrum. We do spectrum analysis. Spectrogram is used to check the voice signature, whether it is matching or not, right? But sometimes clever people may mimic so much that unless I try to find at the log level, when I convert any data into log, it becomes linear, isn't it? If you remember, the sound is proportional to r square, inverse of r square, 1 by r square, right? When I take r square log, it becomes linear. So that is what we are looking at. Something may be visible in linear. So we try to combine both spectrum and cepstrum analysis, not just one alone. If it is one alone, it is spectrum analysis. But when it comes to MFCC, Mel frequency cepstrum analysis, there are plenty of things which we will discuss later when we take out the features of a sound wave, features of an audio signal. We try to get how cepstrum analysis is a feature engineering method. Spectrum is a representation method.
Got it, sir.
Yeah. Okay. We'll break here for some time, right? What I would like to do now is I shared a couple of papers. So I want you to take each of them one. So the paper is, this is the paper I want you to read now. So please read this paper, right? 20 speech analytics use cases to help you succeed. Each of you take one. Right, I want you to take one, and I know you won't read. Sorry for that, but you have to read now. So that's an experiment I would like to see. I have read all of this, and I would like to question you on how you have read, what you have read, how do you build a system. Then we will take that and we try to build a sample system throughout this module. I want each of you to take one use case out of this. You can open this and please go through that. Let's be back by 2. And by that time, I want you to be reading and presenting what exactly you have understood. And even if it is handwritten, just take a snap of it and present it. Yeah, then we will go for whatever you have discussed now. Can we put that into practice? How do we read a file? How do we create a sine wave? How do we create a cosine wave? How do we combine? How do we combine multiple frequencies? Because cosine wave has a different frequency and different alignment, and sine wave has a different alignment, and we'll combine them, and then we try to see how it sounds like. What is the sound of a sine wave? What is the sound of a mixed wave? Let us see that. Then we will take a sound and we try to analyze what are the things that are possible. How do we get spectrogram? How do we get other things, right? How do we get a correlogram and things like that? We will discuss, we'll put the hands on. Possibly some extension of chapter 1 and 2 from Downey's book, right? And some additional things from the papers is what we are implementing. Okay. But the thing that I'm interested now is each of you take one. Whatever it is, you take that, you read that part and present your system design. How do you design this system? Don't worry. If you don't know what is to be done, Google it. But I want you to build your systems. Yeah. Again for it, or you want that to be taught? That should not be taught. That should be experientially learned.
Okay, sir.
I'm not hearing loud sound. Bhartish, you are giving this challenge to me? To me? I will do two systems. Okay. Okay. I'll be back. Let's connect around 2 then. Right?
Okay.
Sir,
When we back,
sir,
yeah.
one question. Sorry to
No,
interrupt
no
you.
problem, Gopi.
Is it everyone have an assignment that which they can pick up, or any two can pick up one?
No, 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 no. Only one. Each of you had to pick up one, and we will go on extending this. Your final assignment will be presented in that way. I want you to present today, because as seen the moment out of sight, it's out of mind.
Sir, actually, our website, the link that which we got now, it is not working, sir. It's getting 404.
I will share this with you all.
Sure, because I can share the
No.
screen. Dashboard is not working, or something is problem with
No
Riva.
I will share it with everyone.
I just share the PDF, sir.
Yes, yes, I'll share the PDF.
I have put it in the chat.
I don't know whether I can share it in the chat, but let me send it in the mail itself.
Sir, you can share in the chat itself, sir. There is an attachment like tag.
I think Bharat
Right,
shared it.
it's not coming.
Oh, it's not allowing you. Okay.
No,
I think Bharat was did
Yeah.
share the document to everyone.
Okay.
Bharat is the one that which? Okay.
Anyway,
Yes,
I'm
that
sharing
one
it
is
again.
able to open. Yes, yes.
You will get it now. Yeah. I sent it. It's done.
Okay. Thank
Yeah.
you.
Okay, select one, dig some deeper insights and present it as 1 or 2 sliders. No need to put anything in PowerPoint and things like that. Write it in a A4 size paper, take a snap and upload it. Right. That you can paste in PowerPoint and present. Okay. Yeah.